Hello ladies and gentlemen, good to see you again. Thanks for tuning in today for what is the 6th lab, and it's going to be accompanying the previous lecture, which was the 8th lecture. And today we've been focusing on inferential statistics and hypothesis testing. So what we're going to be doing today in this lab is we're going to be picking up on some of those statistical tests, two in particular that we covered within the lecture. And you'll remember in the lecture that I gave you the math for how you actually carry out the formula calculations for estimating the test statistics, and we covered some high-level examples for how we would generate certain outcomes that allowed us to make decisions regarding the hypotheses that we previously stated. So today we're going to be picking up on those. We're going to be going back to those 6 steps that are important in hypothesis testing, and we're going to be actually calculating how we do those stats within the code. And we're going to be doing that manually line by line based on those equations which I presented previously, and then we're going to just be validating those manual calculations that we produced using some of the inbuilt packages that are available just to produce statistical tests very quickly, just one line essentially, and it'll be able to produce the result that you're after. As I mentioned in the lecture, the reason why we're doing this is that we've gone from the math to some basic examples previously. Here we're going to do the manual calculations, and I'm going to show you how the packages work, and that's because in reality we're going to use the packages for most of the research that we do. It's quick, it's easy, it only requires a couple of lines. You're interested in getting the results and writing papers, but before you can easily use those packages and know what's going on, you have to make sure that you understand how to calculate these types of stats manually, and that's why we're doing this today. Okay, so without much further ado, let's get into the code and let's start trying some of those examples. So you'll remember that what we need to do first is state the null and the alternative hypotheses. We then need to select the appropriate statistical test, which is going to depend on your data and whether the data that you have actually meet a range of assumptions that are required for certain statistical tests. And then finally, we'll need to determine the level of significance, delineate the regions of acceptance and rejection within the distribution of potential values, calculate the test statistic, and make a decision. Okay, and they're 6 fairly simple steps when you look at each one of them, but I appreciate it's a lot of information to absorb. Please look at the book, the McGrew et al. Book, because that accompanies this work, and actually this week it's very, very similar. All the examples are from directly in the book, so if you go to page 142, for example, you'll be able to follow this along, and I hope that you'll be able to download this code now and run this code in our studio on your machine and understand exactly what's happening as we go through these individual steps. So let's start with a sample of difference of means test, and let's use the example that's in the book, which is on the average energy expenditure of households in this fictitious town, Middletown. So imagine that we take 2 different samples from Middletown households, and we go out and we basically ask people how much they spend on average on energy, and we do that across a variety of different households. These 2 samples essentially have different numbers of households within them. So the smaller sample has 25 households, and it had an average expenditure of $1,810. And it had a standard deviation of $196. Okay. We then also have a larger sample of 250 households, and they had an average expenditure of $1,821 with a standard deviation of $192. Now we're going to carry out the tests for both of these samples. You'll notice, of course, the difference is the sample size, and therefore, depending on the sample size, you're going to need to use different distributions. So, in terms of the national picture, a national survey finds that across the US, the average household expenditure on energy is about $2,000, okay, per household. Now the research question as a consequence: is Middletown significantly lower than the American average? That's what we're interested in finding out. And I think the important word within that question, which hopefully you noticed, is lower, because what that's doing is it's indicating that we're going to be interested in a particular direction within the overall distribution. Okay, so if you were just saying, is Middletown significantly different from the American average, then that would be two-tailed. You'd be interested in whether it was significantly different in terms of it being higher, so in the upper end of the distribution, or lower in terms of the lower end of the distribution. In this case, we're just interested in one direction, just whether Middletown is significantly different in terms of it being below the American average. Okay, so let's progress with the first sample. We need to state the null and alternative hypotheses. We're going to focus on the larger sample first. It's got over 30 samples, so we're able to use the normal distribution, the Gaussian distribution, and that means that we need to pick the right functions within R in order to generate the numbers that we want. So firstly, let's state the null hypothesis. Well, the null hypothesis is that Middletown is not significantly different from the national average. So basically, the mean for the sample is essentially the same as the mean for the total population. The alternative hypothesis is that the mean for the sample is below the American average. Okay, and obviously these are complementary, so it can only be one of these two outcomes, and the test that we're going to carry out will either reject the null hypothesis or will not find enough evidence to reject the null hypothesis. So let's set up some of our variables. So first we need to set the sample size for the larger sample, and obviously n is usually indicative of the larger sample, of the sample size. I've put L here as well to indicate it's the larger sample, so NL is equal to 250, the households that were sampled up here. We then need to get the mean of the larger sample, which was $1,821. So we enter that in as XL. And then we need to get the standard deviation of the larger sample. So that was $192. So we enter that into the global parameters as well. Then we need to allocate the population mean, which we know from the national average is $2,000, so we allocate that to mu. Now we need to think about the test which we're going to use, and I already mentioned that as we're interested in finding out whether this value, this sample in this place is lower than the national average, would be interested in a one-tailed test. And as we're comparing just a single sample against the population, it's the sample difference of means. And as the sample size is larger than 30, we can use a normal distribution, which means we'll use a z-score. We then need to specify in step 3 the level of statistical significance that we're looking for, so an alpha value of 0.05. So we want to be 95% certain that, 95% confident in the result that we achieve if we are to reject the null hypothesis. So that's really important. You should be picking up by now the fact that there's certain linguistic ways to phrase how you use and report these tests, so that you're definitely adhering to the way that tests have to be used, the assumptions, and what we say about reality. Step 4, we need to now identify that Z critical value, and we've done quite a bit of this before in terms of finding out where the proportion of the values may lie in a distribution. So we did this in probability, we've done it in sampling, looking at confidence intervals, for example. And what we need to do is to find the critical threshold when 95% of the values are above that point, so it's the lower bound. And usually what we do is we use Q norm, as we're interested here in getting a z-score for a sample that's above 30. And you can take a look at Q-norm. I've just entered this into the help function here. We've covered this in previous classes, so you'll be able to, hopefully you're familiar with this, or you can look at how we did this in previous lectures. But essentially what we're doing is we're saying, give me 95% of the values that fall in the upper tail, okay? And I appreciate that me just stating lower tail equals false here isn't particularly useful for you for your understanding. When I looked at this, it wasn't clear how you would understand what this meant. So as a consequence, I've just taken a couple of lines of code here to kind of give you a bit more understanding. So hopefully when you run through this, you'll be able to see what happens when lower tail is set to false and lower tail is set to true. Okay, so when we run this code, which is the right code, we get a z-score of minus 1.64 standard deviations below the mean. So this means that 95% of the values fall above this point. Okay, and that's because we're interested in the upper tail value here. That's why lower tail is set to false. If we had set lower tail to true, or if we just not entered any lower tail argument, by default it would just have produced this number, which is 1.64 standard deviations above the mean. So why does it do that? Well, as I say, by default it gives you the area below the given. Sorry, with lower tail true, it gives you the area above the value. Sorry, no, with lower tail equals true, it gives you the area below the value, which is not what we're after here, essentially. So essentially, if we'd got this value, then it would have been the 5th percentile of the scores, rather than the 95th percentile, which is what we wanted. So anyway, the point is that you're able to run these different lines of code and see the different answers that it produces. So this is the one that we want. This gives us the right lower boundary, and it's the same as running Q-norm 1 minus 0.05, okay? Now, I appreciate that that is not that easy to visualize, and I'm a visual person, so I'd much rather show you what I mean by drawing these critical boundaries on the distribution, and then hopefully that's much clearer. So think of what we've done here within the correct version is give me 90% of the values that reside in the upper tail. So let's plot that. So if I generate a curve, so this is a normally distributed set of data, and then if I add in the critical value that we've got, here is the lower bound for the minus 1.64 standard deviations below the mean. And essentially, now we've got this value, what this means is that all of the red part is the area where we would be able to reject the null hypothesis. Okay, we'd be able to be 95% confident that we could reject the null hypothesis. So there would only be a 5% chance that the result had just occurred by random. And essentially, it's important that we use this minus 1.64 value here, because if we got it the wrong way round, so if I just generate the z critical value using the lower tail in the wrong direction, and then I rerun it, you would see that we basically ended up with the wrong part of the distribution. And therefore, that doesn't adhere to the point of the question. Within the question, we're interested in is the sample significantly lower than the American average? Okay, so we need to be at that bottom part of the distribution. So if I just run this again for you, now hopefully you can see that this is the rejection area. And we did cover this within the lecture. So this is for a different alpha value, but it gives you the point that this is our rejection interval down here. and here we wouldn't reject the null hypothesis. And that's the point of taking this particular approach. So hopefully that's more visual for you. So we've been through step 1, which is to state the null and the alternative hypothesis. Step 2, we've identified the test that we need to use based on the type of data that we got. Step 3, we've set the significance level. Step 4, we then delineated the regions of rejection. So that's what we're doing here. We're identifying that if the mean lands within the red zone, then we would be able, given the confidence level, to reject the null hypothesis. And now what we need to do is we need to calculate the test statistic. Okay, so let me just go back to the lecture slides, and I can show you the math. So to get our Z or T score, we need to subtract the population mean from the sample mean, divide it by the standard error of the mean. This is how we calculate the standard error of the mean. So it's the standard deviation divided by the square root of the sample size. So I hope that equation is relatively clear to you. Now let's do it. Okay. So we've got the sample mean here, XL. We've got the population mean, mu. So that gives us the numerator of the equation. We then have SL. So that's the standard deviation of the larger sample. And then we divide it by the square root of the number of sample points within the larger sample. Okay. So when we do that, we get a numerator of -179, and we get a denominator, which is the standard error of the mean, of 12.14 essentially. So when we calculate that by dividing the two together, we get -14.74. So that is quite a strong signal. So the Z calc that we actually obtained is very large in terms of the magnitude of the Z critical value. Yes, so the Z critical value, if we go back to it, was -1.646, so 164. Whereas the Z value that we got was -14.7. So this is a pretty large signal. So the value that we got, the Z value, is in the region of rejection. It's in fact so far in the region of rejection we didn't even include we didn't include that part of the distribution. So we limited this distribution to +4 and -4. So actually this particular value would be all the way over here in the bottom part of the tail distribution. So given that result that we've got, we're now able to say we reject the null hypothesis and conclude that the evidence exists that Middletown households have lower energy expenditures than the American average at the 95% confidence level. So you'll notice there that we're wording it in a specific way. We've got enough evidence to reject the null hypothesis. I hope that's clear. Let's go through it one more time. This time we'll go through it with the smaller sample. So let me just clear the workspace here. And you'll remember that we had the larger sample, which we went through first. So that's where we had 250 households. Now let's work through the smaller sample, because obviously we've only got 25 households. And we discussed in the previous lectures, when we're sampling, if we don't have more than 30 data points, then it's not advisable for us to use the normal distribution and z-scores. So we'll have to use the t distribution and the t statistic. So we're going to use a different distribution here. So here we have the one-sided one-sample difference in means test, and we have the sample size of 25. And then we have the smaller sample mean of $1,810 as the mean energy expenditure. We have the standard deviation for the sample of $196, and we have the mean expenditure of the population, so the national average, which is $2,000. So let's state the null and the alternative hypothesis. So this is very similar to before. Essentially, the null hypothesis is that there's no difference between our sample and the rest of the population. So the mean energy expenditure would be $2,000. Whereas in contrast, the alternative hypothesis is that the sample has a lower mean than the national average. We're going to select the tests, but this time, although it's one-tailed because we're looking in the lower part of the distribution, and because it's a one sample difference from another, it's the same statistical test. The difference is that we're going to be using the t distribution. We use the same statistical level. Let me just run all of this so we've got it in the global environment. There we go, we've got all of our variables entered now. And now we can start to think about delineating the regions of rejection. So we need to first find the critical t value. So this is one-sided, we're looking in the bottom part of the distribution. And because we've got less than 30 samples, we're using the t distribution. So in contrast to before where we use Q norm here, this time round we're going to use a different function, and that's the function for the t distribution. So let's type qt, which should provide us with the quantile value in the t distribution. So hopefully you've seen this before. We've run through this, and essentially what you need to provide in this instance is the probability value that you're interested in, which is 0.95 here, and we need to state the number of degrees of freedom that's required for the t distribution. The degrees of freedom is one lower than the total number of samples. So you'll remember from the lecture, hopefully, that I explained the way to think of the degrees of freedom is that if you're allocating soccer players onto positions on a pitch, you've got 11 people on a particular side, you'll allocate all of the players on the field first, and then as you get to the goalkeeper, the last player to allocate, that player is unable to go to any other position because all the other positions are filled, and therefore there's no degree of freedom for allocating the goalkeeper. And that's why you would always have one fewer than the total number of samples as the number of degrees of freedom, because the last allocation of the last data point doesn't have any room to move. And we'll talk in more depth about why this is important later in the class, but it's required for the t statistic here, the number of degrees of freedom, so you need to make sure you input it. And then also, we've specified that we're interested in the amount of samples that are above this point, essentially. So the lower tail value is treated as false. We covered that in the previous example. I'm not going to cover it again. You can run the code there and make sure you understand what's happening for yourself. So the t critical value in this instance is minus 1.7 standard deviations below the mean. So let me just plot that for you. So we're able to generate a curve, the normal distribution, and I'm able to use the t critical value to add in the red area for the rejection zone of the null hypothesis. So this is the area where we would have 95% confidence that the result hasn't just occurred by chance, and that we'd be able to reject the null hypothesis at that confidence level. So that is the delineation of the region of rejection. In this case, it's a single region because it's a one-tailed test. Then we need to calculate the test statistic, and we've done this previously. So we need to take the population mean from the sample mean and divide it by the standard error of the mean. And that gives us our t-calc. So that's our t statistic. So the t-calc in this example is again much larger in magnitude than the t critical value. So let's just show that. So the t critical value was minus 1.71. That's this value just down here where my mouse cursor is. And the test statistic that we got was minus 4.8. So actually we're just off the edge of the graph here. So again, we're in the rejection zone. So as a consequence, as we're in the zone of rejection, we reject the null hypothesis and conclude that evidence exists that Middletown households have lower energy expenditure than the American average at the 95% confidence level. So we state we are rejecting the null hypothesis, we state what that basically means, we're stating the alternative hypothesis, and then we state the confidence level at which we were able to make that statement. And that's really important, so make sure you follow that defined structure. So for the savvy people among you, you may have noticed in the last example I skipped a little bit of code. I didn't mean to, but I didn't want to get diverted from the path upon which we'd set. But basically, for each of these manual calculations, we can use an inbuilt test in R which shows us the automatic calculation of these statistics. So here, basically, the tsum.test. Let's enter it into the help menu to see what it says. This is a summarized t-test, and basically, if we run this, we're giving it the sample mean, we're giving it the sample standard deviation, we're giving it the number of samples that we have, and the population mu. We're telling it about the direction of the effect that we're interested in. We think that it has a lower impact. We think that there is a lower impact, a lower mean than the national average, and we're giving it the confidence level. And when I do that, it basically spits out the automated results for what we just calculated manually. And what we end up with for the t statistic is minus 4.84, which is the same as basically what we calculated manually. So we know that the calculations that we carried out by hand are correct. So that's good. And just so we don't get sidetracked, I just wanted to run that for the previous example that we had. So this was the largest sample. We've run all of the results and we've got that. You'll remember that the Z value that we got for the sample mean was minus 14.7 standard deviations below the mean, which is quite large. And let's just compare it now to the automated way that we can generate this test statistic, which is using the summarized Z test. And when we do that, we get a Z score using the automated approach of minus 14.7, which is basically the same as the manually calculated Z score that we got. So that's good. It means that we're doing things right. The way that we're calculating it manually in the code is the same as the way that it's been automatically calculated by the package that's inbuilt in R. So if you don't have this package, you need to make sure that the first time you install it, or the first time you run it, you need to run this line of code, install.packages paswr, and then you need to load it into your current environment. So you need to run require paswr. I had actually already loaded it into my environment in advance, so I didn't run that code this time round, but you will need to. So I think that that's looking fairly good. Essentially what we've done is we've recapped on those 6 steps. We've gone over the example that's in the book and we've tested the sample based on one that's quite small, and as a consequence we've had to use the t distribution, and we've used a sample that's quite large, and therefore we've been able to use a normal distribution and a Z score. Hopefully that gives you a good understanding now of those tests, because we've calculated them in the lecture, we've calculated them manually here in the code, and we've actually regenerated the results using the automated functions. Okay, so let's move on now. So previously we were using mean values, so we're using continuous values, and that has a different set of assumptions to, for example, if we had a proportion that we were interested in testing. So you'll remember here we had these certain requirements. So for the mean test, we had to have random sampling, the population had a normal distribution, and the data was interval or ratio based. When we use the one sample difference of portions test, the requirements are slightly different. So we do require random sampling still, but the difference is that the variable is binary. Okay, and in this particular example in the lecture, we were talking about the number of families that had children under 18. Today we're going to be looking at a similar example, but essentially we're going to be talking about the one that's in the book, so you can go down and look at that page. It's in the chapter that we're focusing on at the moment, and it's basically focusing on the proportion of households that are in negative equity. Okay, so I think the reason why this has been chosen as an example is because the version of the book that was produced here was produced not long after the global financial crisis, so that was 2008. It started in 2007, it got really bad in 2008, and it was all related to the subprime mortgage lending market. So basically people who, once the interest rate that the Fed set went up high, they wouldn't be able to keep up with the mortgage repayments on their loan. So for example, if interest rates are low, you might be paying $2,000 a month for your mortgage, but as the interest rate went up to 4%, you might have to pay $6,000 or $7,000 per month, and at some point it means that you might end up with negative equity. So that means that well, firstly, it means you might not be able to keep up with the repayments, but secondly, negative equity is where the value of your home drops below the size of the mortgage that you have, and therefore you just wouldn't continue to pay for the mortgage as a consequence. And what happens there is the bank repossesses your home and tries to sell it on the open market. But the problem with this was that there were so many homes that were going on the open market that it led to a financial crisis because there was a lack of liquid financial cash, basically, within the financial system. Anyway, so that's a quick overview of what the global financial crisis was and the subprime mortgage lending market. If you want more on that, you can just Google it into Wikipedia, and it will just give you a very comprehensive overview of the types of issues that we were dealing with. So now we're in recession from coronavirus. The previous recession that was caused globally was from the subprime lending mortgage market. So anyway, the point is that in this example, we're interested in looking at how many people may be termed underwater, so essentially having negative equity on their mortgage. And this actually, if you're a local city planner, or if you're a decision maker at a local government department, this is obviously a huge concern. I mean, it's not only bad for the local economy if lots of people suddenly made homeless or they become bankrupt, but it could severely affect the taxation that you get from property taxes. And that's a big consideration. So local government revenues may significantly drop in this type of crisis. So we're going to focus on testing these proportions. So you can check out the example on page 148. So Middletown is concerned with the number of housing units which are underwater. They're worried that it's higher than the national proportion. So 85 housing units are sampled, 25 are deemed to be underwater, and that gives us a sample proportion of 0.294. The survey shows nationwide that the proportion is 0.228, so about 22 0.8% of households. So let's state the null hypothesis, and that would be that the sample mean is essentially equal to the population mean. There's no difference. The alternative hypothesis is that the sample mean is significantly, sorry, not sample mean, the sample proportion. So let's just restate that. So for the null hypothesis, we're talking about the sample proportion being the same as the population proportion. Whereas the alternative hypothesis is that the sample proportion is higher than the national proportion. Okay, great. Now we've specified those, let's put the variables into the global environment. So I'm just going to clear what we've got here in the global environment currently. I'm going to enter the sample size. I'm going to enter the number of households which are deemed to be underwater, so in negative equity, and I'm going to get the sample proportion by dividing those two figures. So you'll see that that's 0.294. Now let's enter the national proportion row, which is 0.228, and then we end up with two values here. So we've got the sample proportion and the national proportion. So you can look at the equations within the lecture slides that you've got. So we've just calculated the sample proportion and the population proportion here. And then what we will also need to do is we will need to calculate the standard error of the proportion as well. So this denominator here we calculate by taking the square root of this division. So that's step one. Step two, we need to use a test which reflects proportions. We've got a large enough sample to use said test as well. This is written about in detail on page 149, so you can go and have a look at that. We're going to set a standard statistical significance, which is 0.05, so we want to be 95% certain that the result that we obtain if we reject the null hypothesis hasn't just occurred at random. And as I mentioned before, this is fairly standard for most spatial science, the 95% confidence level. We need to delineate the regions of rejection, so we can go to Q norm and we can say we want the 95th percentile, and this time we are interested in the proportion of values that fall in the lower tail, so we're saying lower tail equals true. It gives us a positive Z score of 1.64. So this should all be familiar to you from the previous examples, but let me just plot it. So what this means, as we're interested in whether the proportion is higher than the national proportion, we're interested in this zone here that's in red. So this is the zone where we would reject the null hypothesis if the proportion ended up in this particular area. So we need to calculate the test statistic now. So let's just do that by getting the standard error of the proportion. So it's this particular calculation just here. When we do that, we get a standard error of 0.0455. Now we can enter that into our test statistic. So we can subtract the population proportion from the sample proportion, divide it by the standard error of the proportion, and that gives us this zcalc value of 1.45. So let's look at those two different values. So the critical value was 1.64 here, and the value that we actually get for zcalc is 1.45. So you'll notice that zcalc is smaller in magnitude than the z critical value. So it's not actually in the region of rejection, it's somewhere down here in this white part. Therefore, we failed to reject the null hypothesis, and that means that we basically don't have enough evidence at the 95% confidence level to show that Middletown's underwater rate is any different from the national average. Okay, so I hope that the way that we reached that conclusion was clear to you. If not, then look at the lecture slides, rewatch this video, and then if you still don't understand even after looking at other materials on this, then reach out to me and I'll be happy to assist. So let's just confirm that calculation by using one of the inbuilt tests. So here we're going to be using prop.test. So let's have a look at the help menu for that. So essentially this is the test of equal or given proportions. So we're dealing with a binary outcome and we're dealing with proportion. And this is the appropriate test to use. So when we give it the mean, the number of samples that we've got, and all the other variables, we're able to examine the output that we achieve. So if you look at this value, you'll see that the chi-squared value of 2.11 is what's being provided. So the prop test function doesn't actually do a z-test in this case, it does a chi-squared test, which I will get to in future lectures, particularly if you're interested in doing survey work. This is pretty important. But this is based on there being one categorical variable with two states. As I mentioned, it was a binary approach. And this is essentially the same thing as the z-score, only it's squared, okay? Which means that we're able to get the z-score by taking the square root of that particular value. So let's do that, and when we take the square root we get 1.45, which marries up with the z-calc that we calculated manually. So we know therefore that the manual calculations that we carried out for that previous example were correct, and we've been able to show that we can use one of the inbuilt packages to generate exactly the same results. So that's really important, and I think that that's a really nice way for you to kind of see how you do these calculations manually, even if in reality once you progress after this course and you always use the automated packages, at least you know then that this is the way that it's calculated and this is the math that's being used to get to that particular point. Great, so that concludes the sixth lab for GGS 300. Do reach out to me if you've got any questions or queries. I hope you'll be able to download this code and run through it properly. There is also the accompanying assignment, which is due, it will be a week on Friday. So make sure that you start that early and reach out to me if there are any issues. So thanks again for tuning in, and I look forward to seeing you again soon. Thank you.